Hi guys, welcome back to my geometry tutorials. Today I want to go over parallelograms and rectangles. So a parallelogram is a quadrilateral with parallel opposite sides. So I've drawn this parallelogram ABCD, and we know that side AB is going to be parallel to side CD because they're opposite sides, right? And segment AC is going to be parallel to segment BD because those two segments are opposite sides of the parallelogram. Just to let you know, a diagonal is a segment that joins two non-adjacent vertices in a quadrilateral. We're just hold on to this definition for right now. Um, you'll see this later on when I do some demonstrations with parallelograms and rectangles, but just remember that it's a segment for right now. Okay, so let's go over this first proof. So we're given that segment AC is parallel to segment BD, and that segment AB is parallel to segment CD. And I want to prove that segment AC is congruent to segment DB, and segment CD is congruent to segment BA. So I'm going to write down what I know, and I know that a segment is a subset of a line. So if you have two segments that are parallel, if you extend both those segments in either direction, they stay parallel, right? So the lines are going to be parallel. Line AC is parallel to line BD, and line AB is parallel to line CD. So if we look at the figure, if we um, have this transversal AD, then angle 1 and angle 2 are going to be alternate interior angles, right? Because the angles are in the interior region bounded by lines AB and line CD, and they're both on opposite sides of this transversal. In a similar way, angle 3 and angle 4 are also alternate interior angles because they're in the interior region bounded by lines AC and BD, and they're both on opposite sides of the transversal. So we know that if a transversal intersects two parallel coplanar lines, that the alternate interior angles are going to be congruent. So I can, since we know that side AB is parallel to side CD, that angle 1 is going to be congruent to angle 2 because they're alternate interior angles. And since side AC is parallel to side BD, that angle 3 and angle 4 are going to be congruent because they're alternate interior angles, right? So if we look at segment AD, well, it's going to be congruent to segment DA, right? Because of the reflexive property of congruence. Remember, if two segments are congruent, then they both measure the same length. So it's not going to matter, if we measure the length of segment AD, it's going to be the same as measuring the length of segment DA. So in other words, which direction we take doesn't really matter for that. And then I can apply angle side angle postulate with statement 7, 9, and 8, and we get that triangle ACD is congruent to triangle DBA. So just as a kind of heads up here, I said that direction doesn't matter when we're comparing congruences between segments, but when we're doing congruences between triangles, the order definitely matters. So just try to remember that whenever you do these types of problems. So I know the corresponding parts of congruent triangles are congruent. So I know that segment AC is congruent to segment DB, and segment CD is congruent to segment BA. So I can immediately establish this first property, that opposite sides are congruent in a parallelogram. Now let's go over some more properties about parallelograms. So I'm given this parallelogram ABCD, and I want to prove that angle ACD, so this angle here, is congruent to angle DBA, this angle here, and the angle CAB, this angle here, is congruent to angle BDC, this angle here. So I'm going to write down what I know. I know that ABCD is a parallelogram. And using the property we just established in my last slide, I can write down that segment AC is going to be congruent to segment DB, and that segment CD is going to be congruent to segment BA, because opposite sides in a parallelogram are congruent. So now I'm going to draw segment AD, so I can do that because you can draw a segment between two lines. And then I'm going to use the reflexive property of congruence. Segment AD is congruent to segment DA. I'm going to apply the side postulate to statements 2, 3, and 5 to get triangle ACD is congruent to triangle DBA. We know that corresponding parts of congruent triangles are congruent, so using this ordering here, we know that angle ACD is congruent to triangle DBA. So we've already proved this first relation here. This is why ordering is so important when you're doing congruences between triangles, because if the letters don't match up in a certain way, then you're going to get something wrong when you apply the corresponding parts of congruent triangles or congruent part. So now I'm going to draw segment CB, and I can do that because the segment can be drawn between 2 points. And I'm going to use the reflexive property congruent. Segment BC is congruent to segment CB. And then I'm going to use side postulate to statement 2, statement 3, and statement 9 to establish that triangle CAB is congruent to triangle BDC. And then by corresponding parts of congruent triangles, we know that angle CAB is congruent to angle BDC, which is the second congruence we wanted to prove. So what does this all mean? Well, if we look at angle ACD, where is ACD? Right here, and angle DBA, well, these angles are on opposite sides, right? They're opposite angles. So we can establish the second property, that opposite angles are congruent in a parallelogram. Okay, so let's take a look at this parallelogram again, and we want to prove that segment OA is congruent to segment OD, and segment CO is congruent to segment BO. So this is where we talk about diagonals. Remember, a diagonal is a segment that joins two non-adjacent vertices in a quadrilateral. So what are non-adjacent vertices? Well, they're basically, so consecutive vertices would be like AC, right? Or AB. So AD would be two non-consecutive vertices, right? And if you draw a segment between these two vertices, then you would get a diagonal. Same thing for this diagonal CB, right? A is a consecutive vertex with a vertex with C, and D is also a consecutive vertex. So B would be the only non-adjacent vertex. So when you draw CB, we get a diagonal for this figure. So okay, so I'm going to write down what I know. I know that ABCD is a parallelogram, that's given. And we know that segment AC is congruent to segment DB. And I can use the reason that opposite sides in a parallelogram are congruent. So I'm going to draw segment AD, and I'm going to draw segment CB. And I can do that because a segment can be drawn between 2 points. We know that segment AC is parallel to segment BD because by the definition of a parallelogram, opposite sides are parallel, right? So then I'm going to notice that angles ACB, so this angle here, is an alternate interior angle with angle DBC, so this angle here, right? Using CB as a transversal, right? And since segment AC is parallel to segment BD, the alternate interior angles are going to be congruent, right? So I can write down that angle ACB is congruent to angle DBC. And I just use the reason that if a transversal intersects two coplanar parallel lines, alternate interior angles are going to be congruent. I'm also going to write down that angle CAD, so this angle here, and BDA, so this angle here, are alternate interior angles with transversal AD, right? So we can establish that angle CAD is congruent to angle BDA. Why are they congruent? Well, we know that opposite sides in a parallelogram are congruent, but we're still using these same two sides, right? AC and BD, and they're parallel, so you can see that they're alternate interior angles, right? Here and here, because they're both in the interior region between segment AC and BD, and they're on opposite sides of the transversal. So we know that angle CAD is going to be congruent to angle BDA. Next, I can use angle side angle postulate to statements 9, statement 2, and statement 7 to conclude that triangle ACO is congruent to triangle DBO. And we know that corresponding parts of a congruent triangle are congruent, so we know that if we look at the ordering here, AO is going to be congruent to DO, so segment AO is congruent to segment DO, and if we look at the ordering here, CO is congruent to BO, so we use that to get segment CO is congruent to segment BO. Again, using corresponding parts of a congruent triangle are congruent. So the big takeaway from all this is that diagonals bisect each other in a parallelogram. So if you have a parallelogram, you draw the diagonals, they're going to bisect each other. So they're going to meet at this point O, which is the midpoint of segment AD and the midpoint of segment BC. Okay, so now I want to move on to rectangles. So a rectangle is a parallelogram with at least one right angle. So let's derive some properties about rectangles. So we'll start off with ABCD is a parallelogram and angle C is a right angle. And I'm going to prove that angle A, angle B, and angle D are all right angles. So I write down what I know. I know that ABCD is a parallelogram and that angle C is a right angle. So if angle C is a right angle, then it's going to measure 90 degrees, right? Because all right angles measure 90 degrees. So we learned in a previous slide that in a parallelogram, opposite angles are congruent. So angle C and angle B are opposite angles, right? So they're going to be congruent. And if we apply the definition of congruence to angles, we know that measure C of angle C is going to be equal to measure of angle B. So we know that measure of angle B is going to be 90 degrees also, since it's equal to measure of angle C, right? And right angles measure 90 degrees. So we can use this fact to get this. We know if a transversal intersects two coplanar parallel lines, then consecutive interior angles are supplementary. So remember, in one of my last videos, I showed that, if two lines are parallel, then these consecutive interior angles, so like angle A and angle C, are going to be supplementary. And if line AB is parallel to line CD, then also angle B is going to be supplementary to angle D. So we can establish that angle C is supplementary to angle A. And what does it mean to be supplementary? Well, the sum of the measures of supplementary angles is 180 degrees. So measure of angle C plus measure of angle A is equal to 180 degrees. We also know that angle D is supplementary to angle B, same reason. So measure of angle D plus measure of angle B is equal to 180 degrees. So if I substitute that the measure of angle C is equal to 90 degrees, and I put that into what I have in statement 8, then I would have 90 degrees plus measure of angle A equals 180 degrees. So if we do a little bit of arithmetic, we get measure of angle A is equal to 90 degrees. In the same way, if I substitute what I have in 6, measure of angle B is equal to 90 degrees, and I plug that into statement 10 here, then I would have measure of angle D plus 90 degrees is equal to 180 degrees. Again, you do the algebra and you get measure of angle D is equal to 90 degrees. So what have we shown? We've shown that measure of angle B is equal to 90 degrees, measure of angle A is equal to 90 degrees, and measure of angle D is equal to 90 degrees. So we know that all right angles measure 90 degrees, so we can establish that angle A, angle B, and angle D are right angles. So that's an important property about rectangles. All 4 angles are right angles. Okay, so this is going to be the last thing I want to go over. So we're given that ABCD is a rectangle, and I want to prove that segment AD is congruent to segment BC. So I start off with what I know. ABCD is a rectangle, and we know since a rectangle has 4 right angles that angle ACD is going to be congruent to angle CDB. Since right angles are congruent, and you know what, we can actually, there's actually 2 ways we can do this problem. I just thought about this right now. You could use, I'm going to use side angle side postulate, but you could also potentially use the HL postulate, which I went over in a previous video, but let's just stick to what I have here. So angle ACD is congruent to angle CDB. So we know since ABCD is a rectangle, well, a rectangle is a parallelogram, right? A rectangle is a parallelogram with at least one right angle. So we know that segment AC is going to be congruent to segment BD because opposite sides of a parallelogram are congruent, and the fact that a rectangle is a parallelogram. Using the reflexive property of congruence, we know that segment CD here is congruent to segment DC. So by the side angle side postulate using statement 4, statement 3, and statement 5, we get that triangle ACD is congruent to triangle BDC. And we know that congruent parts of congruent triangles are congruent. So I know that segment AD is congruent to segment BC. So in other words, since segment AD and segment BC are diagonals of a rectangle, right? I can say that diagonals of a rectangle are congruent. So this is an interesting problem. Actually, why don't you try doing this proof, but using the HL postulate instead of the side angle side postulate that I've done here. So there's a lot of times in math, there's more than one way to solve a problem. So, but definitely look this over and, try to work it out, and try to work it out using the HL postulate. And that's all I have for you guys tonight. I want to thank you for watching my videos, and I'm going to go over some more. I'm going to hold off on the exercises with parallelograms and rectangles. I first want to do a video on rhombus and squares and trapezoids before I actually do problems. So just go over this video. It's a very important video, I think, because I've derived the properties about parallelograms and rectangles, and this will be very useful when we do proofs in the future, because in math everything builds on itself. So I want to thank you guys for watching and hope to see you during my next video. Alright, have a good night everyone. Bye.